Hi. Okay, so this video is going to this video will cover cybersecurity principles, which are ideas that are fundamental to cybersecurity and they're used throughout CyBOK. So first we'll take a look at Salzer and Schroeder principles. So in 1975, Salzer and Schroeder published one of the earliest collections of design principles that were used for creating security controls. So this was actually focused on an engineering perspective. So we're going to look at their 10 principles, and then we'll look at the National Institute of Science and Technology, NIST, look at their principles, which they're a US government agency that provides standards, and their ideas build upon and modernize some of the ideas that Salzer and Schroeder defined. Then we'll look at latent design conditions and what the negative impact of past design decisions can be, and we'll be using something called the Swiss cheese model to make sense of it. And then we'll be looking at the precautionary principle. So this is the idea that we should give consideration to potential problems if we are making changes to a system, especially considering security in this. Like we should give due consideration to the issues that might occur before we deploy. Okay, so Salzer and Schroeder. So they defined 10 design principles for good practice in security control engineering. 8 of these apply to cybersecurity completely, like the primary design principles on the left, and 2 partially apply. I'll explain all of these shortly, and there's a lot here, so I'll go through each of them and I'll try to give some examples to help clear up what's meant by all of these different principles. So first we got the principle of fail-safe defaults. So when we're designing a security control, we should aim, this is the idea that we should always aim to only allow operations that are valid and that are in line with security policy, rather than trying to identify invalid behavior. So you've got so it's basically taking a whitelist approach rather than a blacklist approach to designing your control. You should try and specify what is allowed rather than what's not allowed. So the reason for this is very difficult to identify all the bad configurations up front. Adversaries can get creative, and you can leave loads of gaps if you try and do it the other way, because the problem space is too big, and a blacklist approach is prone to failure. So as an example of this, it's basically saying that you should, unless you explicitly have access to a resource, let's say you were trying, you should be denied access if you've not been explicitly given access. The default should be to fail. So yeah, you would have a list of users that were allowed access to read a file or maybe to log into a system, rather than trying to enumerate all of the options which you should deny. You just deny by default. Okay, so complete mediation. So this is the idea that every time a subject or a person or process tries to access objects, so like a file, a resource, a database, something like that, there should be an authentication check every time you do this. So you shouldn't rely on every single time there's a read on a file, you need to check, is the person or the user or the program that's running, is it allowed to access and read from or write to this resource? So that should happen every time, because otherwise there'll be gaps. There might be opportunities or certain conditions in the program or the system in which you can just bypass or rely on like a previous authentication. There are things like time of check until time of use vulnerabilities, where the permissions might have changed for a certain user, but there'll be like a timing window in which that race condition where you can technically do things which are outside of security policy. So then we've got open design. So this is the idea that a security control shouldn't rely on the fact that the design of the control is a secret. So yeah, this approach of security by obscurity is not good. You can always, if there's a vulnerability within a system and it's private, that doesn't mean that the vulnerability is not there. It just means it's harder for a researcher or an attacker to discover it. But that doesn't mean that it's not secure. Obviously, in that sense, it's just harder to discover a little bit. But you might have an insider who works for an organization might leak the design, or there might be a researcher that's just particularly determined that finds the problem anyway, and you've got a problem. So yeah. Next, we've got separation of privilege. This is the idea that multiple people might be, or multiple subjects might be required in order to authorize access to an object. So, and from a real world idea, there's an example from like nuclear weapons. Back in the day, there used to be requirement that because it's such a highly sensitive thing, launching nuclear weapons, it required multiple people to authenticate it. So there was like keys in a wall that were positioned too far away, so that one person couldn't turn both at the same time. You needed two people. So yeah, this is the idea of separating privileges. So least privilege. All right. So this is an important one that you'll see a bunch around. So this is the idea that each subject, so each personal program process, they should have minimal amount of permissions and privileges that they can in order to perform their role in a business. So I've mentioned this before, so it's like this is all about like describing access controls and roles within a system that would grant permission to do certain things. So as an example, a receptionist at a bank doesn't need full root access to production servers. Text editors shouldn't run as root, etc. So then we've got psychological acceptability. So this is all about interface design, really. How easy is the control to use by the users? It should be accepted by the users. They shouldn't find it difficult or extra work to operate securely. It should be baked into the system in a way that the person that's using it ideally doesn't realize or doesn't have to jump through any extra hoops in order to make it work in a secure manner. So this, yeah, it should be difficult to compromise the security and easy for the users to use. So you shouldn't be able to like disable the security easily or get any like psychological benefits from doing that. So this ties into like human factors. So we'll look at this later in the semester. So we've got least common mechanism. So this is about minimizing the required resources used by multiple users on the system. So resources shouldn't be shared openly between different users. All users shouldn't have unlimited like read and write access to the disk, for example. There can be a lot of problems that way. You usually use like an interface, and yeah, you don't want everybody to have like write access to everything on a disk. So that's obviously a security problem. You need to limit these things and provide interfaces instead. And then economy and mechanism. So this is just about making it as simple as possible, really. Controls should be simple, as simple as they can be, and less complexity basically means there's less room for error and less room for this security control to fail. Okay, so we're looking at things that now partially apply to security. So we've got thing work factor. So work factor is all about like how expensive it is in terms of time and resources to bypass the control. We can look at it from bypassing the control. We can look at it from implementing the control as well. But yeah, it should be so. As an example, password policy is usually a way of it usually aims at increasing the work factor for an attacker, right? So you've got if you increase the complexity and length of a password and you make it more difficult to pre-compute, it makes it harder for an attacker. So an attacker, so does things like adding hashes, using salted hashes rather than just default hashes, because that makes it impossible for an attacker to look up a bunch of pre-computed password hashes using rainbow tables. So all of these steps aim to make the attacker have to work harder to get where he wants. And then compromise recording. So this is just, are there enough, are security events being logged, pretty much? Are intrusions being logged? Are security events being logged? Are we able to actually record that compromise has happened when it happens? Okay, so NIST, we'll look at the NIST principles now. So NIST is the National Institute of Standards and Technology, which is a US organization, and despite the name, the standards are used all over the place. We're using them now in CyBOK, which is primarily British publication. So NIST provide a set of secure standards for design principles for the secure systems, and as part of their system security engineering publication, they build upon the ideas that are described by Sulzer and Schroeder that we just looked at. So you'll notice that there's a few new additions to the list, and some of them have been like slightly reworded. There's things such as the clear abstraction, modularity and layering, partially ordered dependencies, and secure evolvability that I've put on the left-hand side, but there are a few others. But yeah, these four are mostly principles that help with managing complexity. So modern information systems that we've got now with the internet and all of the technology that comes along with it is far more complex and interconnected than it was when Sulzer and Schroeder first defined their principles. So these things are usually, most of these, the ones that I've listed there, are all to do with trying to manage complexity in system design. So there's a few others as well that I've not listed there, but I encourage you to take a look at the NIST standards documents in your own time. There's each of these, there's a table, which is where I got the picture from, and if you click on each of those in the table, it's in Appendix F. If you click on any of the terms, any of the principles, it links you to a definition. So that's where you can get at the definitions. So the link to the slides will be in the description. But for now, I'll just quickly talk through these four. Okay, so the principle of clear abstractions. So this is really very relevant for system design. I've got some examples of what we mean by abstractions. These are things like commands in a command, like for example, a command in a command line application. It could be a function within a program or a class within a program. Could be something like an endpoint on an API that you're interacting with a web application programming interface, that is. So yeah, problems can arise when these things are not clearly defined. So you might have a function which has a specific name, and initially it only did one thing, and then someone's come in and added some extra like side effects that function does that are not have not been described well by like the name of the function or the comment or by the documentation. So problems can arise when these definitions are not of the abstractions are not clear. So modularity and layering. So modularity refers to breaking down your system into different component parts, into like into manageable like self-contained parts. Good example of this is, and this is something that we'll come to in the system security module in detail, but good example of this is PAM, which is a Linux interface which stands for Pluggable Authentication Modules, which is an interface for dealing with different types of authentication on a Linux system. So you might have, so in Linux, if you have a program that wants to do some authentication, it usually talks to PAM, and PAM has a bunch of different modules for, depending on what your authentication approach is, you'll have different modules which enable each of them. So you might have like usernames and passwords, or you might have biometrics, you might have a module for swipe cards, and you can set all these up in PAM so that they all work modularly and they don't interact with each other. They're like all self-contained. You could have things like swipe cards or like Kerberos network authentication as well. And layering is a way of ordering these abstractions so that they're contained and ordered in a sensible manner. So if you think a good idea of a layered system model is, if you're thinking about networking, you'll have probably heard of something called the OSI model, which is just a way of layering the different parts of the network stack. So you have like the data layer and the link layer at the bottom at the real low level. Then further on up you have application layer and the internet layer, stuff like that. Application layer at the top. So yeah, layered systems, it basically contains each part of the it's a way of ordering the abstractions, so that makes sense. Okay, so next we've got partially ordered dependencies. So this is all about making sure that modules which depend on others are ordered in a way that you don't get like one of the modules referring to another that then calls back to itself, and you end up with like a circular dependency. So that this can add a lot of additional complexity. And next we have security. So yeah, like I said, these are all pretty much all to do with dealing with complexity that arises when you're working with systems that are as big as we are these days and as interconnected. So secure evolvability, this one is talking about, kind of ties in back with the image of the camera. from the previous video and the screen in front of it. Just like any developments in your system should, you need to take prior security mechanisms into consideration before you make changes that could remove the effectiveness of that, or impact the effectiveness of that security control or the thing that it was aiming to achieve. So systems should be designed in order to make it difficult to miss changes that disrupt existing security controls. But like I said in that other video, it's not always possible to plan all this up. And I'll just leave my camera off for a second so that you can see the view in the bottom right corner that my head was covering up. Okay, latent design conditions. So this is what I was talking about before, really, when we were talking about secure evolvability. So latent conditions are design decisions that were made, that they're based on design decisions that were made in the past, which, when changes to the system occurred, you couldn't really anticipate, like changes to the system or the environment, when they shifted, you couldn't really anticipate this ahead of time. So as an example, we're looking at, let's think about the Unix security model, for example. So Unix is an old operating system, which was Linux was based on, and it originally was designed and used before the internet, when one computer was typically used by many people at the same time, and they all connected to this same one machine through dumb terminals, which look like this. So there might have been like a room full of these all hooked up to the same machine, and the Unix security model was designed with this in mind, to have like multiple different people running different terminals interacting with the same system at the same time. So as the landscape changed and machines started being connected to one another, the model really for business operations changed from using one system with everyone connected to it to everyone having their own personal machines. And then now really what we're doing with, for example, with the activity stuff is you're all like connecting through a console to one server. That's the virtual desktop environment that's like giving out individual operating systems. So it's changed again, it keeps changing over time, and gaps and limitations that you couldn't, that weren't previously seen as such in the previous environment, then became problems, and they had to be discovered and over time and addressed. So this all kind of ties in nicely with this Swiss cheese model that I mentioned at the start. So you might have heard about this. This got mentioned a bunch of times when the pandemic was going on, for example. So it's a Swiss cheese model. It was described by Professor James Reason in 1990, and it's used all over the place, not just in cybersecurity. It's used to model risk and accidents or incidents. And it's particularly relevant to change the environment, having unforeseen circumstances on security. So when certain developments or settings or configurations of the system are taken, holes in our defenses might align in a way that introduces a vulnerability. So you can think of each layer of cheese as a security control, which is protecting an asset, which is usually data in our case. And in order for an adversary to get to the data, a series of security controls must have been bypassed one way or another. So as an example, you might have had one layer might be a firewall, one might be like your intrusion detection system, then you might have a layer of file access controls for a user. You can also use it as like higher level. You can look at it from a higher level as well. So you can think of it in terms of each slice being, one could be like physical security, then you could have security policy, and network security, and software security. So it's quite a useful way of thinking about what an attacker has to get past and how they've managed to get through all of these lines of defenses in order to actually cause a security incident. So the precautionary principle. So this runs counter to the idea that we sometimes hear that often in like startup culture or in agile development philosophy, that you should fail fast and often. So this actually runs counter to that, really, because the principle suggests making sure that you're aware of the impact of security, of changes that you're making. How does that impact security? Make sure that you're aware of that and you've considered that before you roll it out to a live environment. So it's a pretty simple one. So yeah, as a recap, we looked at sort of Schrodinger's principles, and we looked at how NIST has developed those for the modern era. Then we looked at what is meant by latent design conditions, and finally the precautionary principle. So thank you.